All right, hello class. Thanks for joining with me today, Mr. Harville. Hopefully you're at the right page. But thanks for taking my chemistry class this year. So we're going to kind of start off with some fundamental concepts that do take place in chemistry, a couple of laws and everything, and kind of just give you a brief overview of what chemistry is and what we're kind of going to be diving into later this year. So the first thing we have to ask ourselves is, what is chemistry? There's a couple of definitions that do go out there, but according to Webster's Dictionary, the definition of chemistry is the study of the composition and properties of substances and the changes that such substances can undergo. So it is a study of chemical reactions, phase changes, chemical properties, physical properties, so on and so forth, which we will dive into it. But this is a more generic, accurate definition of what encompasses chemistry. Chemistry is considered the central science due to its position on what's called the science hierarchy. In the scientific community, there is a hierarchy of sciences that is built, and it's kind of built like a pyramid. So the bottom of the pyramid, the foundation of science, is something you guys have probably already dove into, but it's physics. So physics is the foundation of really all sciences. It's the very basic fundamental calculations and laws that governs all that happens in the natural world. And these laws help determine the specific fields of sciences as you go further up. And then in the middle you have chemistry. So chemistry is considered central sciences because it can be applied to both the bottom and the top of the hierarchy. You can use chemistry to define physics. You can use physics to help redefine chemistry, and you can use chemistry to help redefine biology, astronomy, entomology, physiology, anatomy, so on and so forth. So that's why if there's ever any big contributions or new revelations made in the realm of physics, chemists, biologists, and everything, they have to start redefining possibly what they know within their own fields to fit that. A lot of things have been going on in physics in regards to Higgs boson constant, the development of new elements and everything like that, and that's caused chemists, such as myself, to start really rethinking what the chemical world is all about. And so it's very surprising how even maybe slight changes in the foundations can cause huge waves of change as you go further up in the science hierarchy. And at the top, again, it's any other sciences, so biology, everything like that. That's not chemistry and physics, pretty much. So in the field of chemistry, there's two physical laws that are the main foundation of science. The first one is the law of conservation of mass. So its definition is that in a closed system, the mass of an object or collection of objects never changes over time, no matter how the constituent parts rearrange themselves. So, for example, if I took my mouse, let's say this is a closed system, it has a particular mass. Well, if I start breaking this apart, even though that the mass may change shape because the parts that I break apart, it does not mean that the total mass of all those parts put together changes. So that's kind of a simpler way I can think of it. Another way you can kind of think of is the creation of water. So you guys may have been exposed to this maybe in middle school or your freshman year. So we know that we take hydrogen gas and oxygen gas, we put it together, and we make liquid water. So one thing that you can kind of tell off of here, as soon as I can get my... yeah, there we go. So we have 2 times H2. So there's 2 atoms for every molecule of hydrogen gas. So if I take 2 times 2, I have 4 atoms of hydrogen. And there's an imaginary 1 here, so I can just say that I have 2 atoms of oxygen. So these are what's called your reactants on the left-hand side of the arrow, which we'll dive further into this year. We can say that I have a total of 4 hydrogen atoms and 2 oxygen atoms. Okay. Well, when they come together, they do rearrange to go from gas form to liquid form. So they are changing what's called a phase. They change into a different state of matter. But if we take the 2 that's down here, say 2 times 2, the hydrogen's next to it, since it's to the right of this H, it's attributed to the hydrogen. So there's still 4 hydrogens here, and there's an imaginary 1 right here next to oxygen. So I take 2 times 1, and I still have 2 oxygens. So even on the product side, even though there was a phase change and there was a change in molecular composition, the number of atoms that determine that mass is still the same. So the law of conservation of mass is still there. So this is just kind of a very simple example of how the law of conservation of mass plays a big part in science, especially chemistry. So the second physical law that is a foundation of chemistry is the law of conservation of energy. Its main definition is, let's say I have this block, right? I'm going to call it system S. Okay, just define it as a system called S. And if I imagine that this block has impenetrable size, therefore nothing can go in or out, the definition is that in a closed system, the total energy of the system is conserved. So I have this block, nothing can go in or out. But I open up the block, put stuff in it, okay, and make a chemical reaction that makes energy. But the energy can't escape, and there's no energy from the environment that can go in. I can say that since I know what reaction that is, the energy is always going to be the same for that. So let's say I took hydrogen and oxygen, put it in the box, and I made liquid water, and it made a heat change. I can measure that heat, and it will always be the same for that reaction since it's in an enclosed system. So I know that's a little hard to describe through this. We'll try to take a couple more demos in class and maybe a little bit more visualization as we go on through the year. So this is kind of a harder law for students to kind of understand. So I completely understand you may be confused at this point, but that's okay. Feel free to, write down a question on your notes or anything like that. Come talk to me about it, and we can try to describe it in a way that may make a little bit better sense for you, whether you want to do it mathematically or visually, so on and so forth. I'm more than welcome to help you out on that. So let's take a couple examples. Based off these laws, we're going to start making observations in science. So it's important to know when these laws are being conserved and when they are not, and why or why not, based on what system is defined, the environment's defined, what's put in it, so on and so forth. So imagine that you boiled water in a sealed container placed within a vacuum. Would the law of conservation of mass and energy be maintained? Well, before we can kind of break this down, one thing I would highly recommend is in science is that if you're given a problem like this, it never hurts, which you probably know this in physics, is always draw a picture to help visualize what's going on there. So if you need to draw a pot of water and a containment or something like that, anything that makes sense to you, try to draw something to help visualize what this question is asking you. Now, there are a couple of terms in here that you may not understand, which is one of the things you need to start considering some kind of sub-questions. So some questions I would consider is, what exactly is a vacuum? You may know what a vacuum is, but if you don't, I implore you to go and, explore what that is. If you need to go to Google, Wikipedia, a dictionary, a friend, me, another teacher, whatever you want to do, and help define that question. Because if you can determine what a vacuum is, then you can kind of help determine what the parameters of this question are. Like, what does this visually say about this system? Is there any way for the water to escape? So based off if it's a vacuum or not, is there a way for the water to escape? If there is, does that mean it's a closed system? Is it not? So on and so forth. So that helps define if the laws are being conserved or not. And also, can the heat transfer to anything? Is there like some particulars that we need to know about? Does a container need to be made of something for it not to be, transfer of heat? Is there a leak somewhere? Something like that. So what I want you to do is that, it's kind of a vague question for a reason. But what I want you to do is kind of write down your answer, write down the parameters that you think would have to be set for your answer to make sense, and be prepared to discuss it in class. That way we can kind of have a couple of rounds of discussion to see how different systems may act differently. Whoops. It made a noise. Sorry about that. Imagine that you boil water in a pot at your house. So similar thing, but definitely a little bit more generic, but something that you might be a little bit more familiar with. Would the law of conservation of mass and energy be maintained? Why does that keep doing that? Okay, there we go. So things that I would recommend is first, draw a picture. Help visualize what's going on here. And then also start considering a couple of questions. Some questions I would consider, maybe a little bit different from what you would consider, is there a closed system in the scenario? Can you define your house as a closed system? Can you define your kitchen as a closed system? So on and so forth. It depends on how you would set this up. Is there a way to account for any energy transfer? So through the air, through the stove, your kitchen cabinet, whatever. Is there stuff in that? Is your kitchen completely bare, just with a pot with water? It depends on how you define that system. The reason why when you start doing this is because, when we start doing experiments, you're going to want to start thinking about how you need to set your experiments up to start thinking about these little things like, how can I eliminate error? How can I eliminate contamination? Stuff like that. So how you define your parameters of your experiment, how you define the parameters of your system can determine how well your experiment can go. So I want you to consider these questions in these simple scenarios and see how you can help validate some of your predictions, hypotheses, conclusions, so on and so forth. So again, I want you to write your answer down. Take a couple minutes, just kind of label out your reasoning a little bit, and then you bring it to class. We'll discuss it and see what different systems and predictions we can make of this. So a couple of fundamental chemistry concepts we can kind of get from these two laws. Based on the two physical laws of nature, there's a couple of these that we can come up with. First off, matter, which I'm sure you've heard about already from middle school, is composed of various types of atoms and combinations of atoms. So we know that matter has the law of conservation of mass. It's something that occupies space and has a particular mass to it. But even if you break that matter apart to rearrange it into different things, does not mean that the energy is lost or the atom, the mass is lost either. Even though it can be rearranged in different molecules and stuff. So for example, water, rust, which is iron 2 oxide in this case. Now hydrogen peroxide looks really similar to water, but it's not the same thing. So matter can look very similar to each other, but it does not mean it's going to react the same way, act the same way, or be made the same way. So if I set up a chemical equation for making hydrogen peroxide, it would look a little bit different than making water, but the laws of conservation of mass and energy would still be conserved. Same thing with this. So this is kind of more a colloquial reasoning. We can call both of these rust because in the layman's terms it can be called rust, but as a chemist I know that these are two different things that are going to react two different ways because of how they're made up. So even though they look similar, and neither though non-scientists may call it both rust, they still won't react the same way. I know that these two iron compounds, which is the Fe compounds, have two different names. So we'll come to learn that a little bit further on later in the year as well. And again, one substance changes to another by reorganizing the way atoms are attached to each other. So making molecules, compounds, taking hydrogen gas and oxygen gas to make liquid water, so on and so forth. So that's how that can occur. I don't know if you're probably familiar with this. It might have been something you saw in middle school, but this is actually an equation for photosynthesis. So what we know is that we usually give plants water, and we all usually breathe out CO2. Well, this can be reversed to where the plants make oxygen and make sugar for it to live. So that's why we have a symbiotic relationship with plants and why we need plants on the planet Earth to survive, because without plants, they would not make oxygen for us, and without us, we couldn't make carbon dioxide for plants, and it would, we'd all die pretty much. I mean, as morbid as that sounds, but yeah. So this is a very, very important concept, but there are a lot of chemistry and physics that goes into this simple biological process that occurs all the time in the world. But that is it. So if you have any questions or anything, feel free to watch this video again, or write a couple questions down. Come see me in class. We can talk further about it. But I hope to see you next time, and hope to see you soon in class. Thanks.